Okay, let's see how this one goes. This is video number 45, and I'm solving the problem proposed in video number 44, and I'm going to also propose a new problem that we don't know how to do, and then another one that we do know how to do. So in the, as I mentioned in the letter to you this morning, that these would all be problems that concern enrichment, mathematical enrichment. Okay, so the problem posed to you on Friday was I create a circle with a compass, a perfect circle. I measure off 60, 120, 180, 240, 300, 360. I connect the lines and I shade the unoccupied space. And the question would be, what is the ratio of the hexagon, obviously it's a hexagon, to the circle? And we also mentioned, I'm repeating again, that we call it a regular hexagon because it was created in a circle. So that means all the sides are congruent and all the interior angles are congruent. We'll exclude exterior angles for the time being. So there we go. There was the center. And now I have to figure out what the ratio is, one more time, of the regular hexagon to the circle itself, given that the radius is 1. And we agreed that if we know what it is when the radius is 1, I just multiply by a scale factor and I know what it is for all different types of hexagons and circles, as long as they're inscribed as you can see right here. So how do we go about it? Well, if you think about it, when you draw the spokes, or in this case the radius of this thing, and you're going to count the number of triangles you have here, and we agreed that this is 1, and if this is 1, this is 1, and we agreed that the central angle would be 60 degrees, because that's how it's rotating as it goes around. So far so good. We're agreeing that the radius is 1, the central angle is 60 degrees, and this would be 120, this would be 180, etc., okay? And now, if I look at it, I'm going to extract it. I'll do it over here so you can see. And I'm just taking this and extracting 1, because the thought is if I know 1, I know them all. I can just multiply by 6. That's my thought. So let's take a look. I'm extracting this guy. It's an equilateral triangle. Okay? And I'm trying to figure out what's going on here. This angle is 60 degrees, right? But wait a minute. If this is 60, and this is 1, and this is 1, and it's an equilateral triangle, well, this has to be 60, and that makes this 1. So it's an equilateral triangle. That means that the hexagon is composed of 6 equilateral triangles, side of 1. I want to go over that reasoning again. I know this is 60, I know this is 1, and I know this is 1. Well, there are only 2 angles left. These 2 sides make it an isosceles triangle, so it follows instantly that this must be 60 and this must be 60. It's an equilateral triangle. Oh, okay. So now if I can figure out what the area of this is, I'm in great shape. But we did that before. Let's rewrite it over here. Our equilateral triangle, even if it doesn't look that much like 1. 1, 1, 1. Drop the perpendicular bisector to turn it into a right triangle, so I can use the theorem of Pythagoras. A perpendicular bisector, like the word bisect means, cuts this into 1/2, 1/2, and now I have it. I have the hypotenuse is 1 squared minus, right, minus the side over there, or the leg if you like. That's 1/2 squared. And let's do the math here. 1 squared is 1. 1/2 squared is 1/4. So then it's 3/4. Okay? And that, of course, gets the square root. Gets the square root on both sides. We can take the square root of 4, and we end up with radical 3 divided by 2, which is this altitude here, this height. Radical 3 divided by 2. So there we are, so far so good. Next, I have to use the formula for any triangle in the universe. So the area equals 1/2 base times height. In other words, the area equals 1/2 base, which of course, the base of course, which is 1, and the height, which we just calculated, which is 1/2. So the area for this guy equals, we can still see it, equals radical 3/4, as we calculated before. Not a bad idea to do it again. Oh, okay. So I can take all this reasoning now and give myself a little more room here, erasing all this stuff, and extract the number that I want so much, which of course is the area equals radical 3/4 square units. Of course, we're only dealing with units here, although it works with anything you choose. Oh, okay. And now, how many are there? Well, we count again. 1, 2, 3, 4, 5, 6, just like a hexagon. So it's 6 times radical 3/4. But I told you can easily do that kind of work. Reduce the 6 and the 4. And the area of the hexagon is going to equal 3/2 radical 3. You see how useful these guys are? Look what we came up with. We came up with the area of the hexagon. Oh, okay. So area of the hexagon divided by the area of the circle. But we know the area of the circle. That's the easiest number in the world to do. So we have 3/2 radical 3 divided by pi 1 squared. But that's trivial to say pi 1 squared over 1, just to make sure the weak students don't get confused here. So I go here, and I end up with 3 radical 3 divided by, divided by pi. All right, 2 pi, excuse me. We'll need that 2 pi there. Okay, so let's put that all together and see what happens. We put in the numbers on our calculator the way you were taught to do. There's no reason for me to do anything else, and I come up with 82.7 to 1/10%. And that's going to be the answer. And I want to bring up some other things that I'm talking about here. That means, of course, that the hexagon occupies almost 83% of the area covered here by the circle. Now, I want to bring up another thing, just bring it up briefly. I'm going to erase here, and I'll leave the answer here in the corner. Showed you how to do it, all right? I'm going to circle it. And now I'm going to bring up another issue here. Say we wanted to know what it is in units, so we'd have the total of the thing here, which is pi minus 3 radical 3 divided by 2, and that's going to equal some number. I'm going to calculate it, even though I'm not particularly interested in the number itself. I'm interested in the idea, and I clear out here, and I have pi minus 3 times radical 3. Oh, I hit the wrong number there. Sorry about that. Here, we'll try one more time here. Pi minus, the light here is very poor, 3 times radical 3. And I enter that. Divided by 2. And I put everything in there. And I get this number. Let's make sure we got that right here. I get this number, and it's going to be 1 point something or other. The light's very small here. But I want to show you an idea that becomes very important in math as you go on. There was this mathematician many years ago, an ancient Greek, thousands of years ago, and he was looking to calculate pi. And he had an idea, excuse me, and this idea was very simple. He said, oh, what are we going to get if we make it a duodecagon? That's what you call a regular object with 12 sides. And then we fill that in, and the number, as we went up and up, getting the sides more and more and more, is going to tend towards 0. That is the polygon minus, the pi minus the polygon is going to head to 0 as the number of sides go up. And this is a way of calculating the real value of pi. And the gentleman actually did it way over 2,000 years ago to calculate very close to pi by making the polygons have more and more and more and more sides. And when we subtract these polygons from pi, it gets closer and closer to 0. So the number I'm circling here gets closer and closer to pi. Now, if we put this into the calculator here, we do it again, 3 times radical 3, and I enter that, and then I divide it by 2. Okay? The number's 2.59, etc., etc. But this number will be approximating pi as you go up with the number of sides. All right? So, again, since this is math enrichment, how are we doing time-wise? Oh, I'll have to make another one. We're way up there now. I'm going to continue. I'm going to make video number 46, and I'm going to propose your problems to you. But as the number of sides on these regular polygons goes up and up and up, just make a little sketch of it, and now you see it gets closer and closer to being a circle. We figured out a way to see what pi is. So this number will get closer and closer to pi until it actually gets to 3.14, and then even closer as you go on. Will it ever be exact? No, but we don't even know how to calculate pi exactly anyway, since obviously it's an irrational number. Okay, so let's just get rid of this one, and I'll send you a